Hi, I'm Arshia, and this is my Lab 5 presentation, or the last lab for physics. This was a choose your own adventure lab, and I chose one of the options provided, which was the slinky drop. I used Tracker to extract the positions of the slinky falling to the ground, used GlowScript to predict and simulate the movement of the slinky, creating a model based on some prior knowledge, some prior labs, and then some additional stuff, and then I compared both the actual and expected motion. So in Tracker, I just extracted the x and y positions over time, and then in GlowScript, I'd first determine the forces at play, and then the initial positions, velocity values, things like that. Then I velocity and position updated every, delta t, which is within the while loop. And then I also went back, and then I tweaked, I calculated some constants, and I also guessed and checked and tweaked some of the constants at play in this model. So the fundamental principles, the ones that we have done in class are spring force and gravity force, which is two of the three forces that I considered at play in this experiment, but the only two that we've done in physics, and the formulas are given here. And then Newton's second law, which is where we get our velocity and position update formulas from. So yeah, these are the ones that were used to actually create the model and predict motion. The slinky experiment is a man holding a slinky from the top and then letting go of it, and then it falling to the ground. A big observation from the video is that the top drops and then touches the bottom end first, and then they both the top and the bottom end fall to the ground pretty, close together. So the string fully unextends and then falls to the ground, which you can see here in terms of when I tracked it. You see how the y position of the bottom of the slinky, I specifically focused on the bottom end of the slinky in terms of tracking and tracker. So this is constant for the longest time before it finally starts falling. Note that the system is a slinky, the surroundings are everything else. The forces I considered at play were gravity, spring force, and then also air resistance, just from lab 4, because I know that it is at play even though we didn't really discuss it in physics class. And then just side note, I had my axis, the origin at the top of the slinky, where the slinky, was before it was before it was dropped. And the calibration stick, I just looked up the height of the man who runs Veritasium, and that's what I put in. Okay, so the GlowScript model. A lot of these initial values, these are constants, and also I looked up online the mass of a slinky, the usual length of a slinky. I also calculated the spring constant, and I used a lot of these formulas that we've done in class. These two bottom screenshots are from inside the while loop, where you calculate, force, spring, force, gravity, force, air resistance, and then add it up to force net, and then velocity and position update. Significantly with this is I updated both the top and the bottom end of the slinky, because at first I was trying to just update the bottom end because that's the only thing that I tracked, but then that doesn't actually, when you do the simulation, it makes it so that the top is just at a fixed point, but in this case the top is not at the fixed point. Both the top and the bottom of the slinky are moving, and so by updating both the top and the bottom, I was able to simulate a slinky being unextended and then falling. In the exposition, I just, even though the experimental data from Tracker wasn't fully there, I just kept it at 0 because I was focused more on the vertical movement of the slinky. And then the y position over time, as you can see, and again, I just compared the bottom because that was the data that I also had in Tracker. Yeah, it's not fully close together, but it is the same movement, same shape, and it is somewhat close together. So some conclusions and thoughts. Overall, I thought the results were similar. These were about as similar as I could get them, even though they weren't, very close together. One of the main challenges I had was realizing that I should probably update both the top and the bottom of the slinky's velocities and positions in order to get a model that actually somewhat looks like the actual video. And obviously, there was a lot of simplification done. Some of the main errors is, again, Tracker. I'm tracking it myself. Looking back, I perhaps could have also tracked the top, but I didn't do that, so just tracking the bottom kind of simplifies or adds some error and things, and then I also just assume no other work or no other forces. And air resistance, I just fully calculated myself, and fully tweaked the air resistance constant by myself. Okay, so what if we change the spring constant? I was curious what that would do, and what it would do is change the amount of time. Changing the spring constant would make the spring either more or less stiff. If it becomes more stiff or more resistance to being stretched out, the time it takes for the top end to reach the bottom end would decrease significantly. If we make the k constant smaller, then it's not as resistant to being stretched out, so it would take more time for the top to meet the bottom, and yeah. And then the fact that the bottom is stationary for the longest time, I was a bit confused because this was kind of the biggest thing of this slinky experiment. I was confused what it means. What it means is that for the longest time, F net is 0. If we specifically focus on the point at the bottom of the slinky, F net is 0. And what that means is because there's no other forces at play, again, we're going to ignore air resistance in this case, and obviously not spring force because it's kind of the fixed end. So what that means is while the bottom end of the slinky is stationary, tension, I looked this up, but it makes sense. Tension equals gravity, or the magnitude of tension equals the magnitude of gravity, because those are the two forces which we're going to, in the simplified version, we're going to assume are at play. And if F net is 0, their magnitudes have to be equal, which I found really interesting. Thank you.